So at this point, we are ready to define the structure Boolean algebra. A Boolean algebra is a structure consisting of an underlying set with two binary operations, the meet and join operations, one unary operator, that is the complement. This can also be denoted using the overbar. And we have two constants, 0 and 1, and they represent the least and the greatest elements in the underlying poset. Okay, of a Boolean algebra, you have an underlying partial order, and 0 and 1 represent the greatest and least elements. Be careful, not maximal and minimal elements. I'm referring to the greatest and least elements because they must be unique. And for a structure to be a Boolean algebra, here are the axioms it has to satisfy. You have first the identity axiom, x join with 0. Remember, 0 here is the bottom element, not necessarily the familiar 0, not necessarily the false in propositional logic, but it's a generic 0. It's the bottom element. Okay, x join with 0 is x, x meet with 1 is x, same goes for 1. And the complements axiom, x join with its complement is the top element, x meet with its complement is the bottom element. And we have commutativity for both operations, meet and join. And we have also distributivity, which goes, again, both ways. Meet over join and join over meet. Now, these are the four axioms for the definition of a Boolean algebra. Historically, the earlier definitions had actually more axioms, but later on, people have discovered that some of those actually can be proven using these set of axioms. Okay, for instance, domination. X join with the top element equals the top element. X meet with the bottom element is the bottom element, and so on. We have absorption, we have talked about earlier, and we have associativity. And now you see, up to this point, in all of the structures, we gave associativity as an axiom. Here it's not, because it can be derived from these axioms. And in fact, these axioms, although there is no axiom redundant in the setting, meaning that I cannot derive, for instance, I cannot derive identity using the remaining tree, so there is no redundant axioms here. People have been trying to reduce the number of axioms by expressing them in different ways. So we also have minimal axiomatizations with as few as single axioms. I'm not giving those here because, well, first of all, there are multiple of those. And then it's very difficult to see the properties of the structure from such an expression. You have a lot of nands, etc. But it doesn't really paint the picture of what a Boolean algebra is, but you see it much more clearly in this set of axioms. So here's an example. We have the set, the positive divisors of 30. So we have 1, 2, 3, 5, 6, 10, 12, 15, and 30. So the bottom element is 1 and the top element is 30. The complement is defined as 30 divided by x, and the join is defined as the least common multiple of two numbers. And the meet is defined as the GCD, the greatest common divisor of the two numbers. This is the setting, okay? We will show that this is a Boolean algebra. How are we going to do this? By actually showing the axioms are satisfied. Okay, first of all, observe that any number in this set, because it's a positive divisor of 30, can be expressed in this way: 2 to the power a times 3 to the power b times 5 to the power c. And a, b, c here are either 0 or 1. So for instance, 0, 0, 0 for a, b, c gives you 1, 0, 0, 1 gives you 5, 0, 1, 0 gives you 3, 1, 0, 0 gives you 2, 0, 1, 1 gives you 15, and so on. 1, 1, 1 gives you 30. You get the idea. Okay? So in fact, you can actually represent each of these numbers using a 3-bit binary number. But let's not go there right now. But you have to understand every number in this set I can represent in this form: 2 to the power A, 3 to the power B, 5 to the power C, and all ABC here are either 0 or 1. Now first, verify the identity axiom. X joined with 1 is by definition equal to the least common multiple of x with 1, and this is clearly equal to x because the least common multiple of any positive integer with 1 is itself. Similarly, the meet with 30 of x is equal to, by definition, the GCD of x and 30. And since we know that x is a divisor of 30, this will be equal to x because x divides 30, so it's by definition a common divisor with 30. And so identity axiom is satisfied. And the complements axiom, well, x is equal to 2 to the power A, 3 to the power B, 5 to the power C. Then I can write the complement as, remember, A, B, C are either 0 or 1. So take the complement, you get 2 to the power 1 minus A, 3 to the power 1 minus B, and 5 to the power 1 minus C. For instance, 5 is equal to 2 to the power 0, 3 to the power 0, 5 to the power 1. Its complement is 30 divided by 5, it's 6. So it is equal to 2 to the power 1, 3 to the power 1, 5 to the power 0. So whatever you see here, you do not see here, and vice versa. Okay? So this is how you compute the complements. And when you join x with its complement, you are looking at the least common multiple of x with its complement. But you see, due to this observation, x and its complement has no common multiple and no common divisors, right? They are relatively prime. They do not share any divisors because whatever I see in x as a factor, it doesn't appear in the complement, and vice versa. So their GCD, greatest common divisor, must be 1, and their least common multiple must be their product, which is 30. So complements is also satisfied. Recall, 30 here is the top element, 1 is the bottom element. And commutativity, this is trivial because GCD or least common multiple, the order doesn't matter, and they are commutative. And a little bit tricky one is distributivity. Now, to do this, we are going to first of all write the least common multiple of two numbers, x and y, in this way: 2 to the power the minimum of a sub x and a sub y, times 3 to the power the minimum of b sub x, b sub y, times 5 to the power the minimum of 6 c sub x, c sub y. Why is that? Because x is 2 to the power a sub x, 3 to the power b sub x, 5 to the power c sub x, and y is equal to 2 to the power a sub y, 3 to the power b sub y, 5 to the power c sub y. I'm after the least common multiple. So remember, the a's, b's, c's are either zeros or ones. To obtain the least common multiple, if these are both 0, in the result I will have 0. But if I have just 1, it could be 0, 1, or it could be 1, 1, or it could be 1, 0. In this case, I cannot include, well, if it is 0, 1, or 1, 0, I cannot include 2 here. It should still be 2 to the power 0 in the LCM because it's not common. The only way I should include 2 in the least common multiple is both a and a sub x and a sub y are 1. So I'm putting a minimum here. If I see a 0, 0, or 0, 1, or 1, 0, this will be 0. Only if they are 1, 1, then I will put a 1 here. And I will include the factor of 2 in the least common multiple. For instance, let's say 12 and 15. 12 is 2 to the power, well, 12 is not a divisor of 30. It's not in the set. Let's say 6. Okay, 6 is in the form 2 to the power 1, 3 to the power 1, 5 to the power 0, and 15 is 2 to the power 0, 3 to the power 1, 5 to the power 1. Now the least common multiple, okay, least common multiple is going to be, I will include the elements that that will give me the least common multiple from 2, 3, and 5. This should be 2 to the power 1, 3 to the power 1, and 5 to the power 1. And the GCD similarly should be 3 to the power 0 because it's in one of them, but it's not in the other. So it's not going to be a divisor of both of them. Similarly, now the 5, I should have 5 to 0. But in 3, I see both of them, 3 to 1, 3 to 1. So this should be 3 to 1. Okay, now the greatest common divisor in this case turns out to be 3. So based on this formalization, now I'm going to write the least common multiple and the greatest common divisor functions in this way. And this expression here, x join with y meet z, by definition, I write this as the LCM of x with this, which is by definition equal to the GCD of y and z. Now I can write this as the LCM of x, and now I'm writing this per our formalization, 2 to the power the minimum of ay az times 3 to the power the minimum of by bz, 5 to the power the minimum of cy cz, etc. And also I write the LCM as 2 to the power the maximum of the power of 2 in x, which is ax, and this number, which is the minimum of ay az. Similarly, 3 to the power of the maximum b sub x and the minimum of b sub y, b sub z, and so on. So now I have this expression here, the maximum of something and the minimum of something and something. Okay, now this is equivalent to, this expression is equivalent to, or rather equal to this expression. And if you think about this for a while, you can see this. And also remember, all A's, B's, and C's are 0 or 1 here. That's not the key issue here, but if you want to compute this, that will be equal to this quantity here. And it all goes for 3 and 5 powers also. And then you can also write this in terms of the GCD function, which in turn, by definition, can be written in this way, which is equal to, by definition, x join y meet x join z. Okay, so this equals this, and we have now proven the one of the distributivity expressions. The other you can do in a similar way, and by the other I mean x meet y join z distributes x meet y join x meet z. You can show it in a similar way.